This learning target will be broken down into 3 separate videos, learning how to write Lewis dot structures. This first segment of the video will be on how to draw Lewis dot structures for ionic compounds. So essentially a Lewis dot structure is a way to represent on paper what the atom is going to do in relation to its electrons, whether it's making an ionic bond where it transfers electrons or a covalent bond where it shares. So we call these Lewis dot structures, and the first thing you need to know in order to do a Lewis dot structure is how to draw it for an atom. Okay? So for an atom, what we do is we represent every single element on the table, specifically focusing on the ones in the S block and the P block. And what we do is we give them dots for however many electrons they have in their outermost S and P orbital. And luckily for this is there's a trend or a pattern, just like we saw last unit with periodic trends, so that every column kind of has its own number of valence electrons. So if you look at this table, what you can see here is what the Lewis dot structures look like for any given element in the S and the P block. So the first column has 1 electron in the S1 orbital. So the Lewis dot structure would be the element symbol with 1 dot. Second column now has 2 electrons in their S, so it has 2 dots. Now one thing to know is we do represent Lewis dot structures similar to orbitals in that we kind of do the Hund's rule where we put out 1 electron per side before we pair them up. Okay, and I'll show you that in a second, but you can just look at this table and see the trend. Okay, as I go across the periodic table, column 1 has 1 dot, column 2 has 2 dots. Now we skip the D block and go to column 13, which has 2 in the S and 1 in the P, so now 3 dots, 4 dots, 5 dots, 6 dots, all the way up to 8. So what we're doing here is counting how many electrons it has of the octet, kind of already just based on its structure. So let me show you how you produce this for something like carbon. So what I would do is I would write the element symbol for the element I'm dealing with for its Lewis dot structure, so just the big C. And then I imagine that my element symbol is in a box. So you don't have to draw the box, just imagine the box. And if you look at it, you see how we have 4 quadrants, or 4 sides to my symbols. Those are the 4 locations my electrons are going to go out. So for carbon, it has 4 electrons, 2 in the S and 2 in the P, just based on its electron configuration. And so its Lewis dot structure would look like this, with 1 dot on each of the 4 quadrants. Okay, and again, this is basically Hund's rule, 1 per orbital location before I pair up. So if I do an atom that has slightly more electrons than carbon, let's say, for example, oxygen, I imagine oxygen's in a box with 4 quadrants, 1 on each side. And then I look at my periodic table and see that oxygen has 6 electrons. It has 2 in the S and 4 in the P. So I'd put out 1 per side, 2, 3, 4, and then I would pair them up. And the one thing to know about Lewis dot is it doesn't matter where the paired ones are and where the unpaired ones are. Basically, as long as you have the right number for the Lewis dot, you're good. So Lewis dot does not tell us real actual 3-dimensional structural arrangement. It just gives us count. Okay. In terms of language, these guys by themselves right here, these are called unpaired electrons, right? They're not paired right now. These ones that are paired, we usually call these lone pairs. They can also be called unbonded electrons. So lone pairs because they're alone, but they're paired. They're not being shared right now. And then again, unshared because they're not shared. Okay. If this dot eventually bonded up with another atom, so like that dot came from hydrogen, that dot came from oxygen, this right here would be represented by a bond, and now those are a shared pair of electrons. So when we call something a lone pair, those are our pairs that are by themselves. So when it comes to using these dot structures to make ionic bonds, ionic elements transfer electrons from one to the other in order to make ions. So we would take whatever structure we're dealing with. The one on the screen is KCl. Potassium and chlorine make a bond. What I would do then is I would write the structure for potassium and the structure for chlorine. Potassium has 1 electron based on its location on the table. Chlorine has 7. And then I would just figure out how they're going to transfer in order for them both to get their octet. You can use those common ion charges to help you. Potassium wants to make a +1. Chlorine wants to make a -1. So potassium would donate to chlorine, and that would be the new Lewis dot structure. The one thing about this, though, is wherever you have dots and an ion charge, we bracket those. So I'll actually give you the formula for these generally, like this. And then in terms of how to draw the structures, what I would recommend doing is take your formula and write out all of your symbols. So I have 2 sodiums and 1 sulfur. And then I'd look at my table and I'd figure out how many dots I've got on each one. So sodium's in column 1, so it has 1 valence electron and 1 valence electron. And then sulfur is in the column where it has 6. Then I would figure out how they're going to transfer in order to satisfy themselves. So sodium is going to take its 1 and give it to sulfur, so that this becomes a +1. Then the other sodium is going to take its 1 and give it to sulfur, so it becomes a +1. And now since sulfur is gained 2, it's going to become a -2, and I would need to bracket that in. So something as simple as that would be a representation for ionic bonding. I'm figuring out what the charges are and where the electrons are transferring to. From the name, you should be able to figure out what the ratio will be. Okay, so if I'm trying to do one between calcium and chlorine, and I don't tell you the formula, what I would do is I would go to my periodic table and figure out how many dots everything has. So calcium has 2 based on its column on the table, and chlorine has 7. And then I would figure out how to how to transfer electrons so that I get my octets. So calcium wants to become a +2, so it wants to give away electrons. But chlorine can only take on 1 until it's an octet. So all that means is the ratio here is not a 1-to-1. I need another chlorine that comes to the party with 7 electrons for calcium to donate its other 1 to in order to make calcium become the +2 that it wants. So for ionic Lewis dots, the main thing is to end once you have either full shells, 8, or nothing. So the positive ones are going to donate away, and the negative ones are going to take on. And then in terms of that ratio, it's just a question of figuring out how many you need to make it happen. If I'm making a bond between magnesium and oxygen, for example, magnesium comes to the party with 2 electrons, and oxygen comes with 6. So now I would say, well, magnesium wants to get this one away, and it can give it to oxygen. But luckily, it can give its second one to oxygen too. So this one becomes a +2, and this one becomes a -2, and that's it. They now are both satisfied in their relationship. So ionic requires a little bit of work in terms of figuring out like the ratio and exactly how the electrons transfer, but it's really just a kind of like almost a jigsaw puzzle of where these dots go. Okay. That's it for ionic bonding. Have a nice night.